Hello, I'm Will. Welcome to ResearchPod. In this episode, the emergence of life on Earth has been characterized by some as a lightning strike, a foaming tide of primordial possibility, or a moment of divine inspiration. Despite best efforts, the question has remained open for centuries. In a recent analysis that bridges physics, philosophy, and evolutionary biology, Professor Stuart Kauffman suggests the likelihood of energetically favorable groups of molecules synthesizing each other and in turn being replicated as his candidate model. If this seems a bit much to get to grips with, he also made a children's book out of it. So let's start there. Professor, hello.
Hello.
For a little bit of background for the people at home, you have been a doctor, a scholar, a professor, a MacArthur Fellow, and also a children's book author. I've got to ask, wherever do you find the time?
I just turned 80, Will, so I've had a long time. I've been being a scientist since I was 24.
Plenty of time to fit in a great many pursuits then.
I think so. It's been a lot of fun.
Well, starting with that children's book, it deals with maybe one of the more atypical children's stories about the origin of life, or at least the origin of life as we know it.
Yes, it does deal with the origin of life. This starts about 14 hours and 23 minutes after the origin of life, which took place on a Friday afternoon 3.7 billion years ago on a little tidal pool in what is now Western Australia. It was a very hot day.
Well, at least we've managed to nail down the time and keep things good and punctual. So these proto-cells, they have the names Rupert, Sly, Gus, and Patrick. If you could tell us maybe a little bit about them, who they are as proto-cells, and how their experiences together have been an example of really a lot of your work and a lot of your research over the past couple of years coming together into this very exciting field of where it all began.
Let me give you a bit of background before we get to Patrick and Rupert, Sly, and Gus. There's a meteorite called the Murchison meteorite, which landed in Murchison, Australia, I think 1965. It was formed when the solar system was formed, about 5 billion years ago. And it has a high diversity of organic molecules. About 35,000 organic molecules have been detected in the Murchison. And recently, in a flyby of Enceladus, the moon of Saturn, the same diversity, maybe higher diversity, was found in one of the jets coming out from Enceladus. This means that 5 billion years ago, probably throughout the entire universe, with something like a 10 raised to the 22 power stars and solar systems, the universe cooked up a complex soup of organic molecules that were spattered around on planets anywhere in the universe. So, in a sense, the universe was ripe for the emergence of molecular self-reproduction. We don't know quite how molecular reproduction happened, but I and others have been thinking for years that it emerges with the formation of a set of molecules that can mutually catalyze one another's formation out of some simple building blocks. So to use you and me, Will, and Ed, I catalyze the formation of you, Will, out of Will parts. You catalyze the formation of Ed out of Ed parts, and Ed catalyzes the formation of me out of Stu parts. So that's what I would call a collectively autocatalytic set, an idea that's been around for some 50 years.
Mm-hmm.
There's now pretty good evidence that molecular reproduction on the Earth did start with small molecule autocatalytic sets. There's a remarkable article by Joanna Xavier and Bill Martin, now online but not yet published, in which they looked at archaea and bacteria from before oxygen was present, on the order, therefore, of more than 2 billion years ago.
Mm-hmm.
And the analysis of these two cells shows that there's a small molecule autocatalytic set that reproduces itself with no complex polymers in it at all. There's no DNA, there's no RNA, there's no protein, making it very likely that molecular reproduction on Earth started with what we now call as a metabolic autocatalytic set. I'm telling you something that has not yet been reviewed for publication, but it is available online, and I believe that it's correct. If that's true, then the question becomes, well, how hard is it to get a molecular autocatalytic set, given that you've got 35,000 organic molecules? We don't know that now. My own guess is that it's probably pretty easy. So that means that about 3.5, 4 billion years ago on Earth and maybe in the whole universe, reproducing molecular systems of small organic molecules and things like iron-sulfur complexes emerged. That isn't yet life, but it's molecular reproduction. Then the hope is that gets inside of what are called liposomes. If you put cholesterol in water, you get little hollow vesicles called liposomes, and they can bud and divide. And the dream, unconfirmed yet, is that if you get a molecular reproducing system like a metabolic autocatalytic set inside of a liposome, you're on your way to a protocell. And then you need polymers like proteins and so on, and there's theories about that. So that gets us with a squint and a hope to protocells somewhere in some warm little pool in Australia or in deep sea vents. So I've located the story of Patrick and friends in a small pool not far from a volcano in Australia on a Friday afternoon. So that sets it up.
Forgive me if I get this completely wrong, because it's been a long time since I did any chemistry whatsoever. My understanding of physics for molecules was the pursuit of the lowest energy state, and that having an autocatalytic set, does that mean that the catalyzed molecules that they have assembled and continue assembling are a preferential energy state for the raw building materials, or does that require a little extra kick to get them going?
Well, fundamentally, of course, molecules are at their lowest energy state, typically, but this is an open flow system. So let's define chemical equilibrium. Living things are not at chemical equilibrium. There's a constant flow of stuff into you and out of you. You eat food and you eliminate wastes. That is to say, living things are displaced from chemical equilibrium. So here's chemical equilibrium. I've got chemical X that changes into a chemical Y, and Y changes back to X. Equilibrium is when the ratio of X and Y are such that their average concentrations don't change in time. X changes to Y, then Y changes back to X, and they reach equilibrium depending how fast those two reversible operations are. So that's chemical equilibrium. Life is displaced from equilibrium by a continuous inflow of food and energy and an efflux of waste products. So the chemistry is fine, Will. It's that life and living are non-equilibrium.
In the story of Patrick the Protocell and all of his chums, some of these guys do end up becoming food themselves.
Well, they do. Yeah. A deep issue that we're addressing is the following. Let me back up.
Please.
So everybody knows Newton, a fine Englishman, and Newton invents differential equations and integration. Newton gives us 3 laws of motion and universal gravitation. And Newton literally invented how we think as scientists since Newton. And we can call it the Newtonian paradigm. So think of billiard balls on the table. And we ask Newton, what's going to happen, Newton? And Newton says, I wrote down these differential equations. Please give the forces between the billiard balls as they bounce around. And they bounce off the boundaries of the billiard table, called the boundary conditions. Please write down my differential equations giving the force of the balls when they hit into one another, which is essentially their momentum. Having written down the equations and the boundary conditions, state the initial conditions of the balls, that is to say their positions and momenta on the table, and the boundary conditions of the table. Then please integrate my equations, and you will obtain the trajectories of the balls on the table for all time, ignoring friction. Now, to integrate Newton's equations is to deduce the consequences of the differential equations for the trajectories, and deduction is entailment. So Newton's laws entail, logically, the trajectories of the balls. Well, that becomes all of classical physics, and it's the way we've been taught to think. So that becomes the deistic God of the Enlightenment, in which God sets up the universe and Newton's laws, and then Newton's laws take over. And with that, you can have no miracles. So we have the struggle between science and religion and miracles and so on. That gives us Newton, which is determinism.
Mm-hmm.
So this is terribly important because we have all of classical physics from Newton, Then there's an enormous crisis in physics when quantum mechanics is discovered by Planck in 1900. And that entailed an indeterminism, and I think your listeners know this. When you have a radioactive nucleus and it decays randomly in time, implying that there's simply no causal account of when it decays. That's the indeterminism of quantum mechanics. This was an enormous crisis in physics in the 1910 to 1935 era. Einstein always rejected it, even though he proposed the law for the photoelectric effect. Einstein struggled with the indeterminism of quantum mechanics to the end of his days. But quantum mechanics has won. Einstein turns out to have been wrong about some critical things called quantum non-locality. Even though we have indeterminism, which was a big crisis in physics, you still have laws. It's called the Schrödinger equation. And the Schrödinger equation is exactly within the Newtonian framework. The Schrödinger equation is a linear wave equation, and it's deterministic, just like Newton. However, instead of Newton, it gives the deterministic evolution of a probability distribution that something will happen, and the happening is quantum measurement. So up till about 5 to 10 years ago, the standard framework, the main framework in science, was invented by Newton. Its laws, initial and boundary conditions, integrate the equation to get the movement of the system over time, whether it's the whole universe, that's Laplace in about 1810, or all of quantum mechanics and quantum field theory and the standard model of particle physics. Well, we're facing another crisis, and that's actually what we're talking about, Will. And the crisis is the following. In what I've told you so far, there are laws, and then I failed to mention that there's been doubts about reductionism. This is reductionism. It's the view that there's laws down there that entail everything that comes to be in the universe. Mm-hmm. The first doubts about that were by Phil Anderson in about 1975, a Nobel laureate, who wrote an article, More is Different, in Science, I guess it's 1977. And what Anderson argued was maybe properties emerge at higher levels. For example, from quantum mechanics, you cannot predict the wetness of water and what is called the Navier-Stokes equation for incompressible fluid flow. Anderson and later another Nobel laureate, Robert Laughlin, argue that there may be higher level laws that emerge above the lowest level that may be or may not be derivable from the lower level laws, so emergence would be real. But it's even more powerful than that. And the more powerful than that is due to what we're talking about. In 2012, at the École Normale Supérieure in Paris, and his then student Maël Monteville and I published a paper whose title is No Entailing Laws, but Enablement in the Evolution of the Biosphere. I think we're right, Will, and if we are right, it is a crisis in physics as big as or bigger than quantum mechanics, strangely enough, because in the case of quantum mechanics, you could debate whether or not all the laws were still reducible to the Newtonian framework. If we're right, there's no laws whatsoever for the evolution of life, for the detailed evolution of life. So in the absence of any laws, those laws can't be reduced to physics. The becoming of the biosphere is beyond physics. This is the big thing that we're really talking about. Patrick and Rupert and Sly and Gus are an example of it. So perhaps I can elaborate on that.
Elaboration would be very welcome.
It is that the becoming of life is beyond the Newtonian paradigm of laws and entailing conditions given the initials and the boundary conditions.
So there's the possibility that at the underlying level of everything, consequence and cause lose any kind of connection. And what we have is just kind of this potential and actual mush.
It's not the case that cause loses its meaning, but as Giuseppe would have it, for Newton, cause is the deterministic becoming of the universe. In the evolution of the biosphere, we can't have that entailed becoming, but we could still have a notion of cause. it's a differential effect. But let me go ahead so this makes some sense. That all sounds like gobbledygook. So let's raise the following question. Human beings have the human heart. So we can ask, why do hearts exist in the universe? Hearts are very complicated things. To get to the impact of this question, I have to take a slightly strange pathway. The universe starts with quarks and gluons roughly 14 billion years ago, and electrons and positrons and neutrinos and stuff like that. And then we get the Big Bang, and we get the synthesis of hydrogen and helium. Then we get the synthesis in the stars of the nuclei of the stable atoms. Then we start to get chemicals being synthesized. So the central chemicals of biochemistry are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Once you've got those atoms in the universe, you begin to make complex molecules, and not just the organic molecules, with all of the molecules. So we can now ask a funny question. The universe has had time in its almost 14 billion years to make all possible stable nuclei, but has it had time to make all possible complex molecules? And the stunning thing is, it has not. So let me show this to you quite simply. A protein is a string of amino acids hooked together by peptide bonds. A typical protein in you has 300 amino acids. There's 20 kinds of amino acids. So let's just ask for a protein's length, 200. How many possible proteins are there? Well, there's 20 kinds of amino acids in position 1, position 2, position 3, up to 200. So there's 20 raised to the 200th power possible proteins length 200. Well, 20 to the 200th is about 10 to the 260th, which is a really large number. To compare it, the number of particles in the universe is 10 to the 80th. Well, 10 to the 260th is an awful lot larger than 10 to the 80th. Now, the fastest time scale in the universe is the Planck time scale of 10 to the minus 43rd seconds. And if you ask, could the 10 to the 80th particles doing nothing on each Planck time moment but making proteins length 200, how long would it take the universe to make all possible 10 to the 260th possible proteins length 200? And it turns out it would take the age of the universe, say 14 billion years, times 10 to the 37th power. That means the universe cannot have made all possible proteins length 200. And that means something very fundamental. Let me introduce the notion of the word ergodic. It just means that the system can do all of its possible things in the time available. So a gas does that in a small box. It means that the universe is vastly non-ergodic at levels of complexity like complex molecules. That means the universe will never have made all possible complex things. And in fact, recent work, my friend Gabor Vate says, the universe is non-ergodic above the level of about molecules of 500 daltons, which a dalton is the weight of a hydrogen nucleus. So the universe is grotesquely non-ergodic. But that then raises the question, why are there hearts? Most complex things won't exist. Why are there hearts in the universe? And that now becomes a profound question. So let's ask how that can possibly be true. One of the answers is that organisms exist, and for example, since vertebrates with hearts exist, hearts exist, and now why are there vertebrates? Well, that's the origin of life. So let me tell you what a Kantian hole is. It's less mysterious it sounds, but the amazing philosopher Kant, I guess in about 1790, an organized being has the property that the parts exist for and by means of the whole. So you are a Kantian hole.
I have been called worse.
Your parts exist for and by means of you. Your heart exists because it sustains you as an organism, and you exist because of your heart and your liver and all the rest of you. But so's an autocatalytic set that we were talking about before. By the way, autocatalytic sets have been made out of small proteins. So you can get an autocatalytic set of proteins. Gonan Ashkenazi has one with 9 proteins in it in the Ben Gurion. That means, by the way, that molecular reproduction does not require DNA or RNA. So the insistence that life depends upon nucleic acids is wrong. It need not, although it may. Anyway, once you have an autocatalytic set, it's a Kantian hole. So take the case of Stu, Will, and Ed. I catalyze the formation of you, Will, out of Will parts. You catalyze the formation of Ed out of Ed parts, and Ed catalyzes the formation of Stu out of Stu parts. No one of us catalyzes our own formation. The function of a part in an autocatalytic set is to sustain the whole. So the function of one of the 9 peptides in Gonon's autocatalytic set is to catalyze the formation of the next peptide around a cycle, not to jiggle water in the Petri plate. Already you can't reduce biology to physics, because in physics you could talk about all the causal consequences but not specify function. You've got function, and therefore autocatalytic sets gets us to Patrick, and then Patrick evolves and becomes more complex with Rupert and so on, until we have protocells and single-celled organisms like bacteria, like the archaea I mentioned. And the archaea have complex molecules in them. Why do those complex molecules exist in the non-ergodic universe above 500 Daltons? It's because they're parts of autocatalytic systems that bring forth in the universe complicated things like hearts. So we haven't gotten to there's no deductive law. We'll get there in a moment. But as soon as you take seriously the puzzle of why there are hearts, you see that in the non-ergodic universe, living things bring forth complex proteins that could not exist were life not to exist. So we're at a pause spot, Will, before I get to you cannot have laws for it. But is this making sense?
It's a bit much to take in all at once, but I'm going to have plenty of time to listen back to this as I edit, so I'm sure after the 3rd or 4th time through I'll be able to just about make sense of where I am.
I'm sorry. It's hard to make. But I need to tell you a little bit more. Can I go ahead?
Oh, please do. I will just sit back and enjoy the ride, if that's all right.
Yeah, then I'll be quiet with you, turn it into a conversation. I'm sorry. If you poke the corner of a professor, you get a lecture. I'm sorry. So let me just talk about jury rigging. So jury rigging has to do with taking things and using them for purposes for which they were not invented. And it turns out it happens in evolution all the time, in real biological evolution. Darwin called them pre-adaptations. Some fish have a swim bladder that has air and water in the bladder, which tunes neutral buoyancy in the water column. It evolved from fish that had lungs, hopping from puddle to puddle, and water got into some lung. Your function of your heart is to pump blood. But Darwin said, a causal consequence of your heart of no advantage in the current environment could become useful in another environment and be selected. My ridiculous example is your heart is a resonant chamber. The function of your heart is to pump blood, not make heart sounds. I, at 80, have a dominant mutation such that my heart can pick up earthquake pre-tremors. And I'm in Los Angeles, and there's a pre-tremor for an earthquake, and I rush outside, and I survive. Everybody else dies, but I become famous because I survived. And women flock to my side, and I mate with many. And pretty soon there's earthquake detectors in the biosphere. So that's a Darwinian pre-adaptation. So that's what happened with the swim bladder. Now we come to the problem. Could you say now all pre-adaptations that will happen to human beings in our evolution in the next couple million years? Can you feel the question?
I can feel it, but I feel like that would be a gross overstatement of the laws of natural selection and survival of the fittest, because if you're trying to fit for every possible eventuality, then you end up with just wide variety, surely.
Right. It took a long time to find this argument, but let me try it on. These are new uses of things in organisms. So an example which is tied to jury rigging is, I'm going to give you a screwdriver. Tell me all the things you could do with the screwdriver.
Are we counting only the legal options, or?
No. Anything you could do with the screwdriver, including stabbing.
Well, to save incriminating myself or giving away who Banksy really is, I think I better leave most of that left unsaid.
You can screw in a screw. You can unscrew a screw. You can scrape putty off the window. You can tie it to a stick and spear a fish. You can rent the spear to the locals and take 5% of the catch. So that's all. They're perfectly dandy uses of screwdriver. So we now get to something very funny. I'm seriously asking you, well, I've asked lots of people, do you think the number of uses of a screwdriver in London today is infinite, or is it a specific number, like say 73 uses, or is it indefinite?
I'd have to go with indefinite because as soon as someone sees something, there's imitation and variation on the theme.
Right. And everybody agrees with indefinite. It's not infinite because it's not an iterative procedure like 10 to 11 to 12. So the next point that I need to make is there's four kinds of ordering or relationships in mathematics. There's what's called a nominal scale. It's just the names of things like our names. Mm-hmm. There's a scale that x is greater than y and y is greater than z. So that's transitive. X is then greater than z. There's an interval scale like a thermometer where 1 degree and 2 degrees are different than 0 degrees centigrade or Fahrenheit, but 0 doesn't mean anything. Then there's a ratio scale like meter sticks. So what kind of a scale are uses of screwdrivers? Well, it's just a nominal scale. They're different uses, but there's no ordering relationship among those. So that means something important. It means that there is no algorithm, there's no rule-following procedure that can list all the uses of screwdrivers, nor list the next new use of a screwdriver. And that's what's going on with Darwinian pre-adaptations. They are new uses of things for some purposes that allows the organism to survive, and you cannot say ahead of time what those uses are. You cannot pre-state it. And that's going to get us to the big conclusion that Longo and Monteville and I came to. In physics, I haven't said this yet, in physics you can always pre-state the phase space. So when you've got the billiard balls on the table, given the table and the boundary conditions, you know all possible positions and momenta of the balls on the table. So that's the phase space. And the same is true in statistical mechanics. We don't know what the phase space is in biological evolution because the functions of things are part of a phase space of biological evolution. The function of your heart is to pump blood, and that's why you're alive, so it's not trivial. So what Giuseppe and Niall and I realize is that in the evolution of the biosphere, functions are part of the phase space of biological evolution, but we don't know what that phase space is. We don't know what I call the adjacent possible of the biosphere is. And here's the crux point. We cannot write down something like Newton did. Newton's laws are called laws of motion. We can write down no laws whatsoever for the becoming of the biosphere because we don't know what the relevant variables are. We didn't know about hearing 3 billion years ago. We didn't know about the fact that the elephant's trunk reaches the ground and it can squirt water on itself, which is part of why it survives. Over 3.7 billion years, ever new unprestatable functions evolve into the biosphere and change its phase space in ways that we cannot prestate. Therefore, we cannot know the phase space of biological evolution. That means that we can't write down equations the way Newton did. And if we don't have equations in differential equation form, we can't integrate them. And therefore, there's no laws whatsoever for the evolution of the biosphere, which is part of why there are human hearts in the non-ergodic universe. And maybe you can now begin to feel it, Will. It's really big. There are no laws whatsoever. We might be wrong, but I don't think so, for the specific evolution of the biosphere on this planet. And if there are biospheres around in the 10 to the 22 solar systems that are estimated in the universe, which is beginning to appear likely, biospheres are creating all this complexity, and you can't deduce it from physics at all. It's based on physics, but it's beyond physics.
I worry we're nudging up against irreducible complexity here.
Absolutely. It's irreducible complexity. And we don't need, in the irreducible complexity, we don't need intelligent design at all. So that's the end of my lecture. I'm sorry, but it's 40 years of thinking.
If I can get 40 years of thinking squeezed down into 40 minutes of conversation, then I think that's a pretty fair ratio.
Yeah, it's a good ratio. So that's what Patrick and guys are all about. So Patrick gets stuck to a rock because he's got a little peptide that sticks out of him. And because Patrick is in a lagoon with slowly flowing food, the fact that he gets stuck to the rock means that he gets more food per unit time than when he was just floating free. So Patrick has become the first sessile filter feeder in the universe. And so sessile filter feeding has emerged in the universe. And he's Patrick the First, and he's a very sweet little guy. So the point is, Will, what equations would you write down for the fact that Patrick, by sticking to a rock, became the first sessile filter feeder in the universe? You can't. But he did become the first sessile filter feeder in the universe on a Monday afternoon when the sun was shining.
From there, the grander ecosystem and food chain can explode with possibility around him.
Absolutely. That's why I'm very fond of Patrick and Rupert and Sly and Gus. And so now you've got this ecosystem, and organisms create niches for one another, and goods and services create niches for one another. And possible niches are exploding faster than the things that occupy them. So the biosphere explodes in complexity upward in 4 billion years to create all the stuff that's around us, even more overwhelming. Will, we're killing it all. Did you see the UN report about 2050, that 20% of all species will be dead?
Unfortunately, I did.
It's overwhelming, Will. The global economy at 100 trillion a year and growing at 4% is lifting millions of people out of poverty, and it's destroying the planet. We're aware of global warming, but we're not aware of the extinction of it. It's overwhelming. It's the biggest problem humanity's ever confronted.
In a complex world such as ours, when there are finite resources, the value inherent in any life that exists within this ecosystem, being able to see the big picture is a very important and very overlooked trait. So thank you so much for all of your work in generating this very, very big picture.
Will, thank you so much. I'm so glad we've had this time. I'm sorry that I just talked, but somehow needed to get that across. I hope that's okay.
Again, if it takes 40 years to get to this conversation and someone listening to it can get to the end in 40 minutes, I think we're doing everyone else a big favor.
It's a thrill and terribly important.